The Antoine equation is a class of semi-empirical correlations describing the relation between vapor pressure and temperature for pure substances. The Antoine equation is derived from the Clausius-Clapeyron relation. The equation was presented in 1888 by the French engineer Louis-Charles Antoine, 1825 to 1897. Equation: the Antoine equation is log 10p equals a minus bc plus t, where p is the vapor pressure, t is temperature, in degree C or in K according to the value of C, and A, B, and C are component-specific constants. The simplified form with C set to 0, log 10p equals a minus bt, is the August equation, after the German physicist Ernst Ferdinand August, 1795 to 1870. The August equation describes a linear relation between the logarithm of the pressure and the reciprocal temperature. This assumes a temperature-independent heat of vaporization. The Antoine equation allows an improved, but still inexact description of the change of the heat of vaporization with the temperature. The Antoine equation can also be transformed in a temperature-explicit form with simple algebraic manipulations. T equals B a minus log 10p minus C. Validity range: usually, the Antoine equation cannot be used to describe the entire saturated vapor pressure curve from the triple point to the critical point, because it is not flexible enough. Therefore, multiple parameter sets for a single component are commonly used. A low-pressure parameter set is used to describe the vapor pressure curve up to the normal boiling point, and the second set of parameters is used for the range from the normal boiling point to the critical point. Typical deviations of a parameter fit over the entire range. Experimental data for benzene. Example parameters: example calculation. The normal boiling point of ethanol is Tb equals 78.32 degrees Celsius. At this temperature, the two sets of parameters above produce the following vapor pressures: P equals 10, 8.20, 4, 1, 7 minus 1,642.8978.32 plus 230.300 equals 760.0 millimeters of mercury. P equals 10, 7.68117 minus 1,332.0, 478.32 plus 199.200 equals 761.0 millimeters of mercury. 760 millimeters of mercury equals 101.325 kilopascals equals 1.000 atm equals normal pressure. This example shows a severe problem caused by using two different sets of coefficients. The described vapor pressure is not continuous. At the normal boiling point, the two sets give different results. This causes severe problems for computational techniques, which rely on a continuous vapor pressure curve. Two solutions are possible. The first approach uses a single Antoine parameter set over a larger temperature range and accepts the increased deviation between calculated and real vapor pressures. A variant of this single set approach is using a special parameter set fitted for the examined temperature range. The second solution is switching to another vapor pressure equation with more than 3 parameters. Commonly used are simple extensions of the Antoine equation, see below, and the equations of dPPr or Wagner. Units: the coefficients of Antoine's equation are normally given in mmHg. Even today, where the SI is recommended and pascals are preferred. The usage of the pre-SI units has only historic reasons and originates directly from Antoine's original publication. It is, however, easy to convert the parameters to different pressure and temperature units. For switching from degrees Celsius to kelvins, it is sufficient to subtract 273.15 from the C parameter. For switching from millimeters of mercury to pascals, it is sufficient to add the common logarithm of the factor between both units to the A parameter. A pi equals mmHg plus log 10, 10132, 5, 760 equals mmHg plus 2.124903. The parameters 4 degrees C and mmHg for ethanol, A equals 8.20, B equals 1642.89, C equals 230.300, are converted for K and Pa to A equals 10.32907, B equals 1642.89, C equals minus 42.85. The first example. Calculation with TB equals 351.47 K becomes log 10 P Pa equals 10.3291 minus 1642.89, 351.47 minus 42.85 is equal to 5.005727378 equals log 10, 101,328. A similarly simple transformation can be used if the common logarithm should be replaced by the natural logarithm. It is sufficient to multiply the a and b parameters by ln 10 equals 2.302585. The example calculation with the converted parameters, 4K and Pa, equals 23.7836, B equals 3,782.89, C equals minus 42.85, becomes ln P Pa equals 23.7836 minus 3,782.89, 351.47 minus 42.85 is equal to 11.5261636.7 equals ln 101,332. The small differences in the results are only caused by the used limited precision of the coefficients. Extensions to overcome the limits of the Antoine equation. Some simple extension by additional terms are used. P equals exp, a plus bc plus t plus dt plus et2 plus f ln t. P equals exp, a plus bc plus t plus d ln t plus etf. The additional parameters increase the flexibility of the equation and allow the description of the entire vapor pressure curve. The extended equation forms can be reduced to the original form by setting the additional parameters d, e, and f to 0. A further difference is that the extended equations use the e as base for the exponential function and the natural logarithm. This doesn't affect the equation form. Generalized Antoine equation with acentric factor Lie developed a modified form of the Antoine equation that allows calculating vapor pressure across the entire temperature range using the acentric factor omega of a substance. ln R equals ln 27 minus 27/8 omega. T R 9.5663 plus B omega. T R 2.0074 plus C omega. TR 1.1206, where A omega equals minus 0.0966 omega 3 plus 0.1717 omega 2 plus 0.0280 omega plus 0.0498 B omega equals 0.6093 omega 3 minus 1.2620 omega 2 plus 1.3025 omega plus 0.2817 C omega equals minus 0.5127 omega 3 plus 1.0903 omega 2 minus 1.3305 omega plus 0.6925 ln. PV. R is the natural logarithm of the reduced vapor pressure, TR is the reduced temperature, and omega is the acentric factor. The fundamental structure of the equation is based on the van der Waals equation and builds upon the findings of Wall and Gutman et al., who reformulated it into the Antoine equation. The proposed equation demonstrates improved accuracy compared to the Lie-Kessler method.